Hello guys! In this video we are going to talk about determinants. We are going to give you a matrix and you are going to calculate the determinant. So what do we need? To define what is the determinant of a matrix, and we need to know how to calculate determinants of matrices. Requirements. Okay, understand what a square matrix is and operation with real numbers. By the way, a square matrix is a matrix in which we have the same number of rows and the number of columns. Okay? Let's start with these slides. So the determinant of a square matrix is a number. Okay, we are going to assign to any square matrix a number, a value, a scalar. Okay, we transform one matrix into a scalar. Okay, so this will help us to find out if the matrix has an inverse or not. And how do we know that? If the determinant is 0, this matrix has no inverse. If the determinant is different from 0, then we can calculate the inverse of this matrix. We also, with this determinant, we can also find out if the matrix has any row or column that is a linear combination of the others. If the determinant is equal to 0, then we know for sure that the rows are not linearly independent. Okay. So another application of determinants, we can use these determinants in order to calculate the matrix inverse, the inverse matrix of using something that we call the adjoint method. Okay, so for a square matrix, its determinant will be denoted by det A, or just A is like in an absolute value, but it's not. Okay, this is not absolute value. That means determinant. Okay, guys, so determinants are very useful. You are going to apply them many times in algebra in order to find if a linear combination, a set of vectors is linearly independent or not, in order to calculate the inverse matrix and many other things. Okay, so come on, let's start with the easiest case, determinants of order 2. That is, matrices that have 2 rows, 2 columns. The determinant is piece of cake. Okay, in this case, we just multiply the main diagonal minus the product of the secondary diagonal. Okay, A11 times A22 minus A12 times A21. Okay, main diagonal, secondary diagonal. Okay, piece of cake. And as an example, okay, we have here 1, 4, 7, 2. The main diagonal is 1 times 4, it's here, minus the secondary diagonal that is 7 times negative 2. So you just only need to simplify and it's done. In red you can see the main diagonal now and the secondary diagonal now. Okay, so you just need to calculate and that's all. So determinants of order 2, piece of cake, nothing to worry about. Okay, come on, more things. What happens with determinants of order 3? We normally apply something that is called Sarrus rule. Okay, in this case, this is what it's applied on the screen. A determinant of order 3 has 3 rows, 3 columns, and we need to assign a number. Okay, the definition is a nightmare, as you can see. Are you going to remember that you need to multiply these coefficients? No, for sure. Okay, it's impossible, almost impossible. Okay, but the idea is that you can recognize some pattern here, some shape. At least. How do we do that? Okay, the first elements are A11, A22, A33. So the first element is the product of the main diagonal, something that can be easy. Around here, A13, A22, A31, it's the secondary diagonal. So it has something to do with diagonals. Let's see if we can just define what is the Sarrus product, Sarrus rule. Okay, here you have an example. I will try to explain the previous rule with an example. Okay, let's see. In this case, the first element, the first number that we are going to obtain is the product of the main diagonal, as you see here, 1, 4, 3. Then, the next number is this diagonal, but multiplied by the other extreme of the matrix, negative 2, negative 1, 3. Okay, be careful with that. Okay, this is the main diagonal. Then it would be the diagonal under the main diagonal, but the number 3 is on the other side. Okay, then the next one, it's the other diagonal, parallel to the main diagonal, but the third number is on the opposite side, here on 0. So the first three numbers are easy to obtain. Let me recall. 1, 4, 3, 7, 0, 0, and -2, -1, 3. Okay, it's like obtaining a triangle inside the determinant, inside the matrix. Okay, next one. We just finished with the main diagonal and the parallels of the main diagonal. Let's see what happened with the secondary diagonal. Then we multiply the secondary diagonal. Okay, remark, negative. Okay, we are going to subtract the secondary diagonal. Okay, and we are going to subtract the rest of the elements. So this is the secondary diagonal with negative sign. Then I'm going to do the same with this diagonal parallel to the secondary diagonal and this number, and with this diagonal and this number. Okay, let me just show you here. So this is the diagonal parallel to the secondary diagonal, 0, -1, but multiply with the 1. Again, a triangle. And the other one is 7, -2, and 3. That is the other triangle that we obtain in this determinant. We multiply the 3, and remember, negative and negative. We are subtracting those elements from the 3 that we obtained first. Okay? If you don't change the number, then the determinant is not going to be right. Okay, and then you only need to calculate everything, and the final solution is 60. Okay, whatever. Okay, this is the Sarus rule in a picture. I'm sorry because this was a picture. This is positive sign, negative sign. Okay, but the key point is that the main diagonal main diagonal parallel with this number and this parallel with this number, and the negative sign is the same. Okay, so. Okay, now we know how to calculate determinants of order 2 and order 3 only. Okay, be careful because we have no clue how to multiply determinants of higher order, 4, 5, 7, I don't know. Okay, so we need to find out a method to obtain that. Anyway, properties first. Okay, the determinant of a matrix is equal to that of its transpose. Remember that transpose, we are just changing rows by columns. In this case, 1, 7 is a row, then becomes one column. -2, 4, -2, 4, it's a row and becomes a column. The determinant is the same, okay? It doesn't change. Second, if all elements of a row are zeros, the determinant is also 0. The same happens with the columns. It doesn't matter, okay? But if you see a determinant with one row, all of zeros, the determinant is 0. It doesn't matter the shape. It doesn't matter the size. One row full of zeros, the determinant is 0. The same happens with the columns. If you see a column all zeros, the determinant is 0. You don't need to even calculate anything. Just tell me it's 0 and we are done, okay, with the exercise. Okay, if two parallel rows in a determinant are interchanged, the determinant changes sign. Be careful. Let me see. In this case, we have that 1, 7, -4, the product, the determinant is 4 minus 7 times -2 is 18. If I change the first row and I write it in the second row becomes the first row, I just flip the rows, then the determinant is the same value but with negative sign. If I just change the columns, as you can see, 1, 2 becomes the second column and 7, 4, that was the second column, now is the first column, then the determinant is the same value but with a change of sign. More properties. If two parallel rows in a determinant are equal, the determinant is 0. Okay, if you see that 1, 1, 7, 7 or 1, 7, 1, 7, it doesn't matter if you see it by rows or columns. The key point is that if you have two rows that are equal or two columns that are equal, the determinant is 0. You can save time and tell me, okay, that is 0 and I'm not going to calculate anything. Okay? One more thing. But what happens if they are not 0 but proportional, for example? Look at this one. Sorry, no, not in this case. I was going to factor things. I was just thinking in another property. My bad. In this case, if all elements of a row are multiplied by the same number, this number can be taken outside. For example, something that maybe is not so obvious. I have this determinant, 3, 21, -2, 4. If you rewrite this determinant as 3 times 1, 3 times 7, okay, the first row is multiplied by 3. What I can do is to factor 3. and write it outside of the determinant. So this determinant is easier to calculate, and then I need to multiply by 3. This can be done anytime you need, okay? Anytime you see a row or column multiplied by a number, then you can just factor this number outside. Okay, now the property I was thinking about. If two parallel rows of the matrix or columns are proportional, the determinant is 0. It's exactly the same property as before, and we are just mixing some properties. The idea is that, for example, you know that if two rows or two columns are equal, then the determinant is 0. If one is proportional to the other, I can just take this number, I factor the proportional value outside, and then it becomes a matrix with two equal rows or two equal columns, and it's going to be 0. So the idea is that if you see a matrix with two proportional rows, the determinant is going to be 0 directly. Look, for example, this one, 1, 7, 2, 14. If you multiply the first one times 2, then it's just 2, 14. So the second row is proportional to the first one. So this is going to be 0. In the second case, for example, 1, 3, negative 2, negative 6. This second row is the first one multiplied by negative 2. So it's going to be 0 again, okay? Sometimes we don't find out this easily, but it's a very good property. If you just realize that two rows are proportional, then you don't need to multiply anything and you are saving time again. Okay, more things. If all elements of a row can be split into the sum of two terms, the determinant can also be turned into two different determinants. For example, what does this mean? I have this determinant. The first element is a plus a prime. The second is c plus c prime. I can separate the determinant in two. The one with ac bd and the one with a prime c prime bd. So that it means this is a property that we can apply if we want to simplify determinants. If maybe it's too complicated, I can separate it in two determinants. Okay? For example, another property, I was just mistaken again. If any multiple of one row is added to another parallel row, the determinant remains unchanged. BIT property, BIT, very important property. In this case, for example, let me show you here. I have 1, negative 2, and 7, 4. I'm going to add to the first column the second multiplied by 3. It's a really strange movement, but it's very useful at the end. Okay, this is a very important property. The idea is that, again, I'm going to take the first column and I'm going to add the second one multiplied by 3. This is what you see here, 7 times 3 plus the 1, 4 times 3 plus the negative 2. So you have another determinant. This is 22, 7, 10, 4. The key point is that the determinant does not change the value. Okay, so we can just apply some operation that don't change determinants, and this is very important because we will apply it when we need to simplify determinants. Okay, come on, more things. Given a square matrix, a square, remember that is same row, same number of rows and columns, then the complementary submatrix of element A, I, J is the matrix obtained by removing the I row and the J column from the matrix. Okay, for example, let me show you. This one. Okay, I'm going to calculate the complementary submatrix of the element that is in red. So what I'm going to do is to eliminate the row and this column, and we will obtain a matrix that is 0, 3, negative 1, 3. Let me show you. Okay, you have here. I'm just obtaining the complementary submatrix of this element, this 3. So I eliminate the row, I eliminate the column, and the submatrix I obtain is 0, 3, negative 3. These numbers, this number, and this number. Okay? The complementary minor of the element is the determinant of the complementary submatrix. Okay? So the complementary is going to be the determinant of this new matrix. In this case, it's 0, 3 minus 3, negative 1. I change the sign, so it's positive 3. It's a determinant of order 2, piece of cake. Okay, so we have the complementary submatrix that is obtained when we eliminate the rows and the columns, and the determinant that is called the complementary minor. Okay, the adjugate of the element is the number you obtain with the determinant, but multiplied by -1 to the position of the element. In this case, what is the position of 3? Is first row, row 1, and second column, so 1, 2. In this case would be 1 plus 2 is 3, negative 1 power to 3 is negative 1. So it's going to be negative 3 because I obtained the determinant previously. Okay, so this is the value. Sorry, I was calculating it just in advance. Okay, so 1, 2 is the position of 3, so it's negative 1 power cube and negative 3. Okay, more properties. The determinant of a matrix is equal to the sum of the product of the elements of a line, row, or column by their respective adjugates. What are we saying? This is the key point. This is the method we are going to apply to calculate determinants of any order. That is the property I'm going to apply. Let me show you. Here you have a matrix, okay? And we are going to calculate the determinant not by using the Sarros rule, but using a different method, using the adjugates of each of the elements of one row or one column. It doesn't matter. You choose the row or the column you are going to use. Okay? So, for example, in this case, if I decide to choose the second row, this determinant is going to be the first element, A21. Remember that I chose this row. Sorry. So it's A21 multiplied by the adjugate of this element. That would be the determinant of these two and these two. Plus this element multiplied by the adjugate of this element. It's going to be the determinant of A11, A13, A31, A33. Okay, remember that you need to eliminate the rows and the columns of the element you are developing. And finally, plus the element A23 by the adjugate, multiplied by the adjugate of this element. That would be, I eliminate this column, I eliminate this row, so it would be A11, A12, A31, A32, the determinant multiplied by the negative 1 of power to the position. Okay, we will see an example. Okay, example, let's solve it. We are going to take the first column, and why I'm going to do that? Because it has a 0. And remember, this is a hint for the future. Take the row or the column that has the maximum number of zeros. In this case, we are going to develop by this column. So what is going to be the determinant? Okay, here you have 1, it's the element, times negative 1 power to the position of this element. This element is in position 1, 1, so it's -1 power 1 plus 1. If I eliminate the first row and the first column, the determinant obtained is 7, 3, negative 2, 3, the one you see here. Then plus the second element, this is 0, multiplied by the -1 power to the position. In this case, the position is 2, 1, so 2 plus 1. This is going to be 3 on the exponent, negative 1, then power cube is negative 1. And the determinant obtained when I eliminate this column, and this row. It's 3, negative 2, negative 2, 3. So I got this determinant. Okay? Plus, finally, this number, negative 1, multiplied by negative 1 power to the position of this element. This element is position 3, 1. So it's 3 plus 1 is 4, negative 1 power to the 4th power is just 1. And the determinant obtained when I eliminate this row and this column. So 3, negative 2, 7, 3, as you see here. Then you only need to calculate everything and the result is 4. Okay, in general, you can apply this property for determinants of any order. Of course, it's going to be a lot of work, okay? But in these cases, at least we have a method that cannot be applied in any order. Okay, in this case, I'm not going to just use this, I'm not going to calculate it. It cannot even be placed in the square of this slide. It's a lot of work. If you are going to do that, you can just choose, for example, this row exactly, and it's 2 times the adjugate, 0 times the adjugate, 7 times the adjugate, 3 times the adjugate, and also worse because each of these adjugates is an order 3 determinant that you need to calculate using by Sarros rule or the same method. So it's a lot of work. Okay? So guys, more things. The last thing we are going to see. What is the method we are going to apply in order to calculate determinants? So we can create the maximum number of zeros in a line, row, or column and use the properties of determinant. And expand this determinant through this, the row or column that has the maximum number of zeros. Okay? So for example, let me do it really fast. We are going to obtain the reduced echelon form, and we can just apply the property that we saw before. It's going to be easy. I said reduced row echelon form or row echelon form, and it's not necessary. I only need to make zeros on one row or one column. Okay, let me show you. We are going to take this one, and by doing these operations, I'm just subtracting the first column minus 5 times the fourth one. The same here, F3 minus 4, the fourth row. I can obtain this one. It's the same value. These operations don't change the value. But I'm going to obtain something like this. So if I develop the determinant by this column, it's going to be a piece of cake because it's just 1 by the add you get. And then we can just calculate it directly with Sarro's rule. So the process is a little bit more complicated. Obtaining these zeros, it's not easy, okay? But if you do that, it's going to be easier. Yeah, I know, calculating these operations, you need to think twice, you need to make it right and don't make any mistake. But, okay, it's not difficult, I promise you, and it can simplify the process. Okay, what have we seen? We have reviewed the determinants of square matrices, we just saw some properties and calculate some determinants. I know we did it a little bit fast, but if you have any questions, write us, okay? Okay guys, thank you for your attention.